Tēnā koutou, ngā mihi nui ki a koutou katoa, ko Glen Rowe toko ingoa. A very warm welcome to you all. My name is Glen Rowe, and it's my pleasure to introduce this presentation, which is the first of a series of talks for the RASNZ 2020 online conference. For the planned in-person conference, we had arranged a speaker who had been involved in the Event Horizon Telescope project, which produced the first image of a black hole last year. Katie Bouman has given permission for us to use a talk she presented at MIT. In it, she describes the methods and procedures used to produce the first results from the Event Horizon Telescope, a network of telescopes distributed across the globe.
So I'm Bill Freeman. I'm a professor in EECS at MIT and at CSAIL. Just one thing, for an hour from now, we only have this room until noon, so right after the talk, we all have to file out so a class can come in. More recently, I've been known as Katie Bowman's PhD supervisor. She graduated from MIT in 2017. While she worked on her PhD, she kind of did preparation for the future planned data collection for the Event Horizon Telescope. She introduced the Event Horizon Telescope Imaging Challenge, which was a series of 3 different challenges, where basically she brought kind of computer vision rigor and techniques to the interferometry community, and they had bake-offs and sort of controlled, careful assessments of the different image reconstruction methods that were available. Her thesis was called Extreme Imaging via Physical Model Inversion, Seeing Around Corners and Imaging Black Holes. Then she did a postdoc at Harvard with Shep Dolman in the Harvard Center for Astrophysics, and she was in the thick of things with the big black hole imaging result, the image reconstruction, the data reduction. This summer, she'll start as an assistant professor in the Department of Computing and Mathematical Sciences at Caltech. So I'm delighted to introduce Professor Katie Bouman.
Kind introduction, Bill. It's great to be kind of back home, at MIT and tell you about how we were able to create the first picture of a black hole. So before I start, I want to emphasize that this is a huge team effort. I know there's a lot out there that's saying I single-handedly made the first image of a black hole, and that couldn't be farther from the truth. So this is a big effort from many people from many different backgrounds for many years, and that's what really made it possible. So if you go out past the city lights tonight and look in the night sky, you'll see the Virgo constellation. And at the head of Virgo is this giant elliptical galaxy, M87, which is 55 million light years away. And if we could zoom in towards the towards the center of M87 with radio telescopes, you would see this double-pronged jet of radio emission. And this enormous jet, which is shooting out of the core of M87, has been shown to be incredibly dynamic. So its galactic scale arms flail around on the time scale of months. And at the base of this jet, we believe that there is the cause for all this motion is a supermassive black hole, an object so dense that it sucks up anything that ventures too close, even light. And so this black hole is so small that it would fit into that single dot at the base of that jet. But by definition, the black hole sucks up light. So if we were to zoom into this black hole, what would we expect to see? Well, light-propagating narrow black hole doesn't actually follow straight lines. It's curved because the black hole curves the space-time around it. So light wraps around the black hole. It can even do circles around the black hole. And so what happens if you light up the space-time around it? So you have photons flying everywhere, and these photons are curved around. So some of them fall into the black hole, but the ones that just graze it get curved around into a ring of light that you'll see here. So here, for this black hole, you get an almost perfectly circular ring of light. So if Einstein was right about general relativity, this light would bend into a ring where its size and its shape tell us about the mass and the spin of the black hole. And this ring is referred to as the black hole shadow. So simulations of turbulent plasma and the jets in the accretion disk around the black hole predict that if you had an infinite resolution, if you could see at infinite resolution, you might see something like this with all this swirling gas around. And in 2017, we hooked up an Earth-sized telescope, and 2 years later, this is the image we saw of the black hole in M87. So we were so excited to be able to show you these results just less than 2 weeks ago. And today I want to tell you more about this experience in making the first image of a black hole. So what makes taking this image so hard? How did we verify that what we were constructed? And what did we learn from these images? So, why is this so hard? Well, as I said, M87 is 55 million light years away from us. And it's so small that even the Hubble telescope can barely make out that booming jet on the sky. And so people have been trying to zoom into M87 for many years now, but seeing that shadow requires a very particular type of telescope, one that's observing at just the right wavelength and is just the right size. And too short of wavelengths, like optical wavelengths that the Hubble observes at, can't make out that shadow. And at longer wavelengths, the gas that shrouds the black hole blocks the light from within. And so even at a 3 millimeter wavelength, that black hole shadow is not visible. But if you go to shorter and shorter wavelengths, theorists predict that eventually that gas would become optically thin, and you'd be able to see the event horizon. But even though if you could successfully observe at the short wavelength, we face another challenge. So the size of this ring is incredibly small. It's only about 40 microarcseconds in size, which is about the size of an orange on the surface of the moon. And so taking a picture of something that small is incredibly difficult. So if we plug in the wavelength and the required angular resolution into the diffraction limit equation, then we can calculate that in order to take a picture of this ring, we would need a telescope that's 13 million meters across, or the size of the Earth. And if we could build this Earth-sized telescope, we could just start to make out that distinctive ring of light that's indicative of the black hole's event horizon. But although building a single-dish telescope the size of the Earth is impossible, by joining telescopes from around the world, I've been working as part of an international collaboration called the Event Horizon Telescope, which has created the first computational telescope that's the size of the Earth, capable of resolving structure on the scale of a black hole's event horizon. And joining telescopes in this manner is called Very Long Baseline Interferometry, or VLBI. And all of the telescopes in the worldwide network for VLBI work together. So they're linked through the precise timing of atomic clocks, and then teams of researchers at each of the sites essentially freeze the light by recording petabytes of data. And then the computers process the data, act like a lens to make that picture. But how do we actually make a picture from all these different telescopes? Well, unlike with a camera, in VLBI we don't capture the picture in pixel space, but we capture it in frequency space. So we essentially take measurements of the black hole images Fourier transform. And if we tiled the entire globe with telescopes, if we covered it completely, then we would measure all of these spatial frequency measurements. But since we have telescopes at only a few locations, that means we only get a sparse number of sparse number of measurements. And so it turns out that for every 2 telescopes in our telescope array, we get a single measurement of the underlying image's 2D spatial frequency, and that's related to the projected baseline between the telescopes. So the closer 2 telescopes are together, the shorter that baseline and the smaller that spatial frequency, and that allows you to get large-scale structure. So to get the fine structure we need to see that ring, we need to put our telescopes as far apart as possible. But even with the 8 telescopes that the EHT observes with, only 5 of them were at different locations and were actually able to see the M87. So with that only 5 locations, that means we would sample only 5 choose to only 10 points that we would have to try to make an image from. But luckily, as the Earth is rotating, we actually obtain other new measurements. So since the baseline between telescopes change as the Earth rotates, this amounts to carving out different elliptical paths in the frequency plane. And we get these measurements by recording hundreds of terabytes of data at every telescope. So here you see Lindy Blackburn posing with about half a petabyte of data, which is about half the data that we collected at one of the telescopes, the LMT telescope in Mexico. And we record so much data that we can't send it over the internet, and we actually have to send it in planes to a common location. And at that common location, a special purpose supercomputer called a correlator actually combines the data using the precise timing of the atomic clocks. And then once this is done, this is passed on to a calibration stage, which finds weak signals in the data, tunes some parameters to pull out stronger signals. And developing this calibration pipeline for the unique EHT data has been a huge endeavor. So led by Lindy Blackburn, but also a lot with the help of Maciek, Sarah, and Michael, along with others. But they really spearheaded this, effort and made it possible that we could even have data, that we could even make images. So at this point, we have a lot of data, or actually at this point we don't have that much data, and we can abstract away all the astrophysics and look at it as purely a computational imaging problem. So we have this sparse data, and our goal is to find the image that caused it. And if we were given measurements that covered the entire frequency plane, that would be trivial. We would just need to take the inverse Fourier transform. But since we only see a few samples, there's actually an infinite number of possible images that are perfectly consistent with the data that we measure. And so how do we deal with this? Well, the traditional method to deal with this is a method called clean. And clean works by assuming that the data isn't actually sparse, and it puts a 0 everywhere where we haven't observed any measurements. And then you get this, by taking the inverse Fourier transform, you get this kind of messy image here that looks somewhat like the original image, but it's all messy. And so at this point, the method kind of throws away the data, and it iteratively searches for the brightest points in the images, removing artifacts that occur to incomplete sampling. And after it's iteratively found a bunch of point sources like this, then it blurs it together to get the extended source. And so, as I mentioned, this is the default method that is used in radio astronomy to solve these problems. And the method actually works pretty well out of the box when there are a lot of telescopes and when they're observing at really long wavelengths, like this image here produced from the VLA. But for the short wavelengths that the Event Horizon Telescope operates at, getting an image is actually much harder. And there's a couple of reasons for this, but one of the big ones is atmospheric noise. So the whole reason that VLBI is able to work in the first place is due to the fact that light from the black hole is traveling for 55 million years, and when it gets to Earth, it's a plane wave, and it's going to reach one of the telescopes slightly before the other one, depending on the location. And that slight time delay is key for extracting that 2D spatial frequency measurement for image reconstruction. But when you have a different telescope in Chile than you have in Hawaii, than in Spain, they all have different atmospheres over top of them, and that adds an additional delay into the signal. So that adds an additional phase delay into our complex frequency measurement. And similarly, the atmosphere causes different attenuation factors in the signal, causing absolute gain term. Other errors in the measurements that we make also come from things such as pointing errors, being out of focus, astigmatism, and problems in the electronics. And so it turns out, actually, for the EHT, this was particularly a problem for the LMT. Pointing errors were particularly a problem, which was unfortunately the telescope I was at. But so because the LMT was still in the process of being commissioned, it hadn't been finished yet, and so there was no good way of pointing on the source. So what you have to do with a radio telescope is you actually have to point the dish at the source, right? And if you're off by a little bit, then you won't get such a strong signal. And because of this on site, we actually, because we didn't have a good way of pointing, we had to come up with a way on site to recover the location. So what we had to do is raster scan over a patch in the sky and try to figure out where the source was. But you'd get images like this, where because of the atmosphere changing, it's very hard to figure out where the source is. And we came up with simple methods, match filtering methods on site to try to figure out how to point. But even then, for very, very faint sources like M87, it was still incredibly difficult to point. And so we ended up having gain corrections that we had to do that were really large over the course of a night. So ideally, your gain should be around at 1. For LMT, it was quite different. And so all these errors turned out to be quite bad. I mean, and we have this we're supposed to measure this complex Fourier component italicized V. But we get this other completely random phase and often a very different amplitude. And so that's pretty terrible. Basically, if we don't have phase or we don't have amplitude, what do we have? So coming up with an image is kind of hard, especially when, if you took the inverse Fourier transform, you get some scrambled image like this, and you have to try to come up with what is the underlying image. And so cleaning up the scrambled image is really difficult. But actually, if you look at the measurements, you notice that if we had a third telescope, then the measurements that are formed with that third telescope actually share some of those same corrupting terms. You have the same G2 and phi2. And so once we can take advantage of this property of this shared information when solving for our images. So to do this, we developed two classes of imaging algorithms that we've explored in imaging M87. So in the inverse modeling one, it's based on that clean algorithm. But it's also paired with something called self-calibration, where we actually solve for those gain effects, those corrupting phases and amplitudes. And this is a traditional method that is used within radio astronomy, as I said, so that's a really big plus, because that means that it's very well vetted in the community. People understand what's good about it and what's bad about it. But one kind of negative is that because it is often very sensitive, you often have to have a guidance from a knowledgeable user, where they actually lay down what is called clean boxes, which are boxes on the image that show where to put flux in your image, where to put bright points. I just want to highlight three people, Jose, Jaeyoung, and Thomas, who, as I said, this method has been around for a while, but they really help, along with a number of other people, but help to try to get it working on EHT quality data. But then a second approach of methods that we've been developing more recently, and I've been doing this in collaboration with Michael Johnson, Andrew Shale, and Kazuo Akiyama, is on regularized maximum likelihood methods. So in this method, we don't try to find an inverse function that takes us directly from the measurements to the picture, but instead we try to find a picture that both fits the measurements and is also defined as likely under some sort of regularizer or prior term. And so the disadvantage here is that we have to define what is a likely image, and that introduces bias. We have what is likely. But a huge advantage of these methods is that we can naturally incorporate other types of error. And so, for instance, we can naturally incorporate optimize the image with constraints that are insensitive to all those calibration errors I talked about earlier. And we typically do that through constraints known as closure quantities. And so a closure phase, for instance, is when you add up the phases of different measurements in a closed loop. So when you multiply the measurements, these complex measurements, you add their phases, and the additional corrupting terms due to the atmosphere cancel out, and you're left with the term that is the same as if you didn't have any atmosphere at all. And similarly, in a quantity called closure amplitudes, if we divide the measurements of 4 telescopes in multiply and divide them in a certain order, you're left with a quantity that's the same as if you had gains that are all exactly 1. And so both of these closure quantities were determined a while ago, but they're typically used for calibration purposes. However, rather than just using them for the purpose of calibration, we actually incorporated it directly into the imaging. And so our imaging assumed no calibration whatsoever. And so we do this by modeling the forward system as a function f of x that returns these robust data products, the closure phase and closure amplitude, that we'd expect to see if the true image was x hat. And then by computing the data likelihood, we can compare it to the true measurements, and it allows us to determine how consistent the proposed reconstruction is with those closure statistics, and while also being invariant to the error that plagues the original measurements. And through this data likelihood, we also can incorporate other types of error that we expect to see on measurements from the EHT. And then we incorporate this image prior regularizer that allows us to score how reasonable each image is. So we can optimize to find that final image. And so by using this kind of framework, we can actually recover reasonable images even when the data is really poor. So for instance, on the top row, it's showing a ground truth image. This is synthetic data. But in the middle row is as you go along the x direction, it's adding more and more gain error. So in both cases, there is no absolute phase. But as you go towards the right, you've added more absolute amplitude error. And in the middle column is when we constrain the absolute amplitudes in those closure phase. And the bottom row is when we constrain only the closure amplitudes and closure phases. So the bottom row is completely calibration-free imaging. It doesn't rely on any of the calibration. And you notice that although it starts breaking down at about 25% error, when you constrain the amplitudes, we're completely invariant to it when we use only the robust closure quantities. And so this has been a huge development for the project and has allowed us to actually reconstruct images from this incredibly noisy data, even when the full calibration wasn't done. And so, even though we've been coming up with these great methods, the question still remains of how do we actually make sure what we're imaging, we're not biasing our images too much. We have this really sparse, really noisy data, and so all of these imaging methods, whether it was clean or the regularized maximum likelihood, required that we inject some sort of information into the problem to say what do images look like. And so we don't want to accidentally inject information, for instance, that it should look like a ring, and then be excited that we got a ring back in the end. So we need to be really careful with these assumptions. And a while ago, we had this idea that different types of images have different kinds of underlying statistics. Images off your phone look very different from images from Hubble that look very different from black hole simulation images. And so if we could model these different types of statistics, then we could impose them in the image reconstruction. And if we got the same or a very similar looking image, no matter what statistics we impose, then that gives us the idea that builds us our confidence that what's leading the image reconstruction is the data and not the specific assumptions you made. And so in the work that we did for M87, we didn't use this patch idea. We didn't learn statistics from different kinds of images, but we were inspired by this idea by reconstructing images with many different kinds of image assumptions and from many different kinds of users to make sure that no matter what bias you added, we got the same kind of image in the end. And so to do this, we put together this 4-step process. And it was essential that we were very careful when we made pictures because we are working with a new instrument that's never been used before. We're pointing it and trying to take a picture of something we've never seen before, and there's nothing really out there to test to make sure that the telescope is working properly. So we had to be very careful with when we're constructing images and when validating them. So the first step in this process was to actually test ourselves on synthetic data. So what we did, and actually this was not very common in radio astronomy, is that we actually created a synthetic data pipeline where we then took a team of people who generated synthetic data from some sort of image, adding in all the different kinds of crazy noise that we expect. And then this was passed off to a team of people who didn't have any knowledge of what the true underlying source was. And then they were told, OK, make your best guess using your methods. Make your best guess at what the image is. And then these images were passed off to a team of experts that looked at the images and tried to say, from these images, do I believe what I'm seeing? Do I not believe? What parts do I trust and not trust? Which is very similar to the process that we had to do for the EHT data. But then unlike with the real data, we actually have the true image so we can compare it in the end. So I want to show you just a couple of things that we saw in these imaging challenges. So here was one of them. And on the top is the ground truth image. And on the bottom is 5 methods that were submitted done by different people. And notice that they all look different, right? And none of these methods at the time that they reconstructed knew what the true image was. And so by looking across them, you can tell, OK, although they all look different, they all have similarities. So for instance, the left side is bright in all of them. You kind of have this crescent feature. But in only some of them does this little tail kind of appear. So that kind of gave us confidence in certain features and made us unsure of other features. So by looking across images, we can kind of build up confidence, looking at images made from different assumptions in different people. We also tested other kind of crazy things. So here we also tested, I threw in an image of a snowman, which some people were not so happy with. They thought it was like a binary black hole. But it was really important because we had to make sure that our images were able to see something totally unusual too, something that they wouldn't expect. And so I think that was really important as well. So these kind of synthetic data tests gave us confidence in the results, and in the methods, and in the procedure. But still, we wanted to be really careful with the M87 data. So based upon these synthetic data tests, we developed how we were going to approach the M87 data. So we wanted to avoid shared human bias like we had done in these imaging challenges. and that would also allow us to assess common features among different independent reconstructions. So we split up a big effort of people who develop methods, who are just good at using methods. There were about 40 of them, and we split them up into four teams. And the 4 teams span the globe. And 2 of these teams had more of a focus on the regularized maximum likelihood methods, and the other 2 more on those traditional clean and self-calibration methods. And though any team could use whatever methods they wanted, what we decided is, at this point, we still didn't want to just compare the images right away. So we wanted to make sure that when we compared our images, we didn't want to just compare one time and be like, oh, we all screwed up. So what we did is we made a website where teams would submit images here, and then it would provide them with a set of diagnostics that could help them actually see if we were ready, if for instance they were actually the images fit the data as we expected, or if the gains aligned. And so we did all of this, and we tested the whole procedure with these diagnostics before we even started on M87. And what we did is we actually had other data from the EHT, from active galactic nuclei, where you can't see that event horizon, but you can still see the jets. And we tested this team procedure with this blind imaging on those sources, and made sure that that this procedure of independently reconstructing and then eventually showing our images allowed us to gain confidence in that we could converge on similar images. So this is, for example, the image that we saw with 3C279, which is a AGN taken for the EHT data. And notice that doesn't even look anything like this ring structure. So we were able to recover different kinds of structures too. But once we had ironed out the imaging process and made sure that our algorithms could work on this EHT quality data, then we finally released the data of the black hole in June of 2018. And at this point, we were actually working with an engineering release of the data. But it was just actually amazing to see the data for the first time, because if you know anything about the Fourier transform of circles or rings, so on the x-axis here, this is spatial frequency, and then the y-axis is amplitude, and you notice this jump. And the Fourier transform of ring is a Bessel function. And so you get this jump, and so it's very, it seems like there's some structure there at least. Anyway, so at this point we said, okay, everyone had their data, and they go to their separate rooms, and we said, okay, don't speak to each other, and just make your images, and don't talk. And so I remember this moment actually for the group that I was in. I was in team 1, and we all ran to one room, and we closed the door, and we all had our imaging scripts ready, and we pressed go at the same time and watched as the images appeared. And so it was a really fun day. And this was the image that we produced in team 1 at the end of the first day of imaging. But then at this point, we still weren't ready. We wanted to still test to make sure that we had done everything correctly. What was the distribution of brightness along the ring? Do we still believe it was a ring? And so after that, we worked for another 7 weeks completely in isolation from the other teams, not telling them anything that we had gotten so far, even what data looked good or didn't look good. And after 7 weeks, we all converged in Cambridge, Massachusetts, and we revealed our images to each other. And this is what we saw on that day. So this was one of the happiest days, I think, we had in the collaboration, because even though we had reconstructed images ourselves, we had no idea what the other teams would get. And and really seeing the same kind of general 40 microarcsecond ring that was brighter on the bottom than the top come out of all methods really was a huge boost of confidence in this structure. And so this is the image that we produced at the end of that day at the imaging workshop, the average of those 4 images, and all the group of imaging people that really made it possible. But once we had this, even though we had gotten these images, we still weren't sure. Maybe there was still some sort of human bias. We all had been thinking for so long that we would get some sort of ring out, and these did have some human intervention when making these images. So we wanted to figure out, okay, can we break our images? If we remove the human from the loop entirely, can we break them and get something else? And so for the next few months, so these images were shown in July. And so for the next few months, we actually worked on trying to break our images. And the first step we did is we tried to objectively choose parameters. So if we remove the human completely from the loop, do we still get this ring? And what we did is we developed 3 pipelines in 3 different software. One was in diffmap, which is an older software library that focuses on that clean method. And then 2 were libraries written in Python that were specifically developed to handle the EHT image quality data. And they were focused more on regularized maximal likelihood methods. And each of these kind of has its set of knobs that you have to tune to make an image. And so we wanted to make it so that humans weren't selecting these knobs, but we could, the computer would choose the best ones. And to do this, we made a very small toy set of data. And we chose this set, though, very carefully. So one is that actually it wasn't just so we had 4 different kinds of images of toy geometric images, but we actually also added this large jet feature to them to make sure that we actually, because of the fact that our image isn't compact and we have extended flux, this actually adds another layer of difficulty to the data that we have, and we wanted to reproduce that as well. But anyway, these images were chosen for a specific reason, and that's that if you look at their amplitudes, the spatial frequency amplitudes, you'll notice that they all have this jump at about 4 gigalambda. And that is very similar to what we see in the actual data. So if you just look at it from the amplitudes perspective, they all kind of look similar. So for example, if we wanted to train, if we had a disk, and we generated lots of synthetic data with all different kinds of noise and everything from that disk image, and then we have this fake data, and our goal is, okay, well, from this fake data, try to find the parameters that best recover that disk image. And then we transfer this onto the actual real M87 data. We found, oh, okay, even when we tried as hard as we could to find parameters that matched the disk, when you actually run it on the real data, that data forces you to put this hole in the center. And so tests like this were important that we do. But we didn't want to just do it on the disk. We did it on a bunch of these different these geometric sources. And we found a set of parameters for the group of them that would work across all days and all sources. And this is the image that we produced from the EHT imaging library from those trained parameters. And one thing that I was actually really excited about is that for the clean imaging, this traditional imaging that's typically done with people like hand drawing where the boxes should go, we actually, for the most part, did it completely automatically, even with selecting these parameters. So that was really quite nice, too. And so here is for those 3 pipelines on the 4 days that we observed M87, what the images looked like when we recovered the parameters this way. And notice that they all look different. They're all slightly different, but they all recover the same kind of ring structure, brighter on the bottom than the top. And if you notice diffmap is blurrier, that's the clean method, and that's because, remember, as I said, we blur those images. They're actually point sources that are blurred in the end. But we wanted to be really careful what we showed the public, because we are very familiar, for instance, with these images and what kind of things show up as artifacts. And we didn't want people over-interpreting them. So what we did is we actually blurred them to an equivalent resolution. And then we averaged those images together to show the image that we showed at the press conference in the media, so that we were very confident in these features that we're showing. Okay, so once we had even made the images this way, we were still, we still wanted to validate these images. We still weren't 100% sure. And so we went through a series of validation tests. And I'm going to just talk about a couple of them now, but if you go to the paper, you can see some other ones. So the first one, the easiest one to understand, is the independent day test. So we observed M87 over 4 days, and we imaged independently for each of the days, and you see the ring in all 4 days. So that's pretty good. It's not just appearing in one of the days. They all look a little bit different, actually, but you get the same basic structure in all of them. Another validation test that we did is looking at variation across different parameters. So remember when we selected this beta by training on this small data set, but why should one beta be any better than the other? Why should one set of parameters be better than the other? Actually, we feel like there's a whole set of parameters that give us reasonable reconstructions. And so what we did is we searched a huge parameter space and tried to find the ones that such that the normalized cross-correlation between the truth images and our reconstructions were greater than between the truth images and the images blurred to some resolution, resolution of the interferometer, actually. And so that gave us not just one set of parameters, but a whole collection of parameters for each pipeline. And so, for instance, in the EHD imaging pipeline, we looked at about 1,500 images. We surveyed hundreds of thousands. I think probably over the course, millions of images. So here is a slice through two of the parameters in that parameter space for the EHT imaging library. Parameter survey. And so you can see in the green boxes, those are the ones that are chosen from the synthetic data test as being ones that should produce reasonable reconstructions. And one thing I want to highlight about this is actually in this top left corner, that image there is actually produced with no regularization on it at all, except for the constraint that the image has to be positive. So light is positive, so that's a pretty easy constraint to make, and a compact field of view. So that has very little assumptions on it, and you still kind of get that ring structure out in the end, which was quite surprising that we saw. Here's for the Smiley parameter survey, highlighting the ones that it found as in this top set, we called it, and for the diff map parameter survey. And once we have a set of images, like 1,500 images that we have, for instance, in the EHT survey, we can look across them at variations. So for instance, we aligned all those images, and you can see the mean image on the left, the standard deviation in the middle, and the fractional standard deviation on the right. So what the standard deviation is telling us is, where do we have variations in that image? And we noticed that we have variations in these like 3 knot regions. So those regions, you should be a little bit more skeptical of the exact value of the flux that we recover, and that's partly due to the point spread function, actually. But notice that they're still much smaller than the intensity of the light in the of the mean image. And so, and if you look at the fractional standard deviation, you notice that around in the ring is we have very little uncertainty, but then outside of the ring, there's a lot of uncertainty. So, don't believe all the wispy stuff going around, I guess. And so another test that we did is actually just looking at the gains. So remember I told you before that we have these corrupting terms. We lose our absolute phase altogether, and we often lose a lot in our amplitudes as well, although not all the sites lose our amplitudes, and so we can weakly constrain them. And so a lot of times in imaging, so we do, so one thing we do is when we observe, for instance, when we observed M87, we interleaved it with observing that other AGN, that 3C279 I talked about earlier. So we can compare the gains that we recover from the two sources. And so on the bottom is the 3 images from the 3 pipelines of M87, and on the top is images computed from those same code bases for 3C279. And when you solve for what are the best gains, what are those best calibration parameters that would match that image, and you overlay them on top of each other, you see, for instance, for 2 sites here, that the trends generally are the same across these sources. And so it also gives confidence in basically the calibration that we recover through imaging. But remember I told you before that we do have just purely closure phase. We can also just purely use closure phase and closure amplitudes without even weakly constraining the amplitudes at all. And when we do that, when we completely remove the absolute amplitudes from the imaging, we actually still recover this ring image. So remember, this is a completely calibration-free, this closure-only image is calibration-free imaging altogether. We can still recover the image, that ring, sorry. Okay, and then the last thing that we do, or that I'll talk about at least today, for validating is model fitting. So model fitting is a whole paper on its own, so I'm not going to do it justice by a couple slides today. But one thing is, once we recovered these images, or we can also just say, what is the size of the ring that we get across all the different parameter survey, across all the different kinds of images. And so we use very, very simple methods to recover, what is the ring, and what is the diameter of that ring. And once we do it for all of those images, then we can compare their diameters across that set of images and see that across the different methods and across days, we get very consistent diameters across the whole set of images for each pipeline across each day. And so that gives us confidence in also the size of the image that we're recovering, of the size of that ring we're recovering. But we don't just have to, we don't have to recover the diameters directly from imaging. We can just do model fitting directly. So we can fit a ring directly to that data, or a crescent directly. So this is showing a sampling from a nested sampling method, which, so we had an MCMC and a nested sampling method that also tried to model fit to the data directly. So not doing imaging first. And when you do this, you also you get a diameter of around 42 microarcseconds. So this is very consistent with what we got directly from imaging as well. So one question you might have at this point is like, did we, what did we learn? Did we prove Einstein was right? And the short answer is no, but we also didn't prove he was wrong. So, so it's progress. So anyway, for the size of any object, you can actually calculate. So I'm going to kind of tell you about how we kind of can test GR with these images. So for any size object, you can calculate its escape velocity, which is the critical velocity necessary for an object to launch off of it to infinity. And that's the square root of 2, the gravitational constant, the mass over the radius, right? And notice that this doesn't actually depend on the mass of the object you are launching. And so what happens if the escape velocity is more than the speed of light? Well, then not even light can escape, and you get this dark star or the black hole. And so if you take a fixed size mass from this, and from this equation, you can calculate the particular size you need to compress down that mass to get a black hole. And this critical radius is called the Schwarzschild radius. But actually, generally what we expect is we don't actually see this ring. So we don't actually see the event horizon itself, but we actually see, what we expect to see is the radius at which photons are orbiting essentially continuously around the black hole. But actually, we don't even observe this exact photon orbit. What we observe is the lens photon orbit. So because gravity is so great around the black hole, that photon orbit is actually lensed, and it becomes bigger for us. So for a non-spinning black hole, the diameter is actually 5.2 times that Schwarzschild radius. And if the black hole is spinning, maximally spinning, is 4.8 times it, so it's a bit smaller. And so this range of radius that we'd expect for that photon orbit would kind of defines what we would expect to see for canonical general relativity. But notice that this directly actually depends on the mass of that black hole. So for a smaller mass black hole, this becomes smaller. And why that is interesting is because actually for past measurements of M87, it was actually quite unclear what the mass was. So gas dynamics pointed us towards a mass of around 3.5 billion solar masses, while stellar dynamics, bulk stellar dynamics, looking at the stars orbiting, pointed us more towards 6.6 billion solar masses. And stellar dynamics provided an upper limit, as there could be more mass within the stellar orbits, but than just the black hole. But we wouldn't expect there to be any ring bigger than that yellow ring there. But then we could also ask ourselves, okay, well, how do we turn this into a test of GR? Well, we could also look at other unusual exotic objects. So for instance, wormholes also produce shadows. However, wormholes actually have a feature that's much smaller for the same size mass. So you can see here for the 6.6 billion solar mass here, it's showing the blue dotted line is a wormhole shadow you would get. And for naked singularity super spinning black holes, they also produce shadows, but they're also even much smaller. And when you lay the EHT image on top of all these, you instantly see that out of all of these exotic possibilities, we're left with a ring that matches nearly perfectly with the stellar dynamic measurements of the black hole for canonical GR. So, what exactly is this mass? So we can take this equation for the diameter and relate it back to the mass quite easily. But remember, this diameter is the photon orbit that I talked about. And that's a very particular orbit. And if you look at a bunch of simulations, you notice that some of the emission is actually not from if you blurred them to a ring, most of it is actually not due to the photon orbit, some of them, but due to all the kind of the gas around it or inside of it. And so it's hard to know exactly what is the photon orbit. So these were done by groups at Radboud, UIUC, Frankfurt, Harvard, and Perimeter, all these different kind of GRMHD simulations of what we'd expect a black hole to look like. And then by simulating data from them, like what we expect the data from the EHT would look like with all the different kinds of crazy noise, and then doing feature extraction on this data, we could come up with a diameter and calibrate it to the true mass over diameter measurement this way. And by doing this, for each of those 3 methods, for doing geometric crescent model fitting, for fitting directly to those GRMHD simulations, and by doing feature extraction in the image domain, we saw no matter the way that we recovered that diameter, they were all consistent with one another, and they were consistent with that stellar mass measurement that we had. And I just want to highlight a couple people here who really helped do this calibration and recover this mass. So Avery Broderick and a number of his students and postdocs, although I want to highlight Paul, Don Pesci came up with new methods. Jason Dexter and Ferriozel did a lot of the work here. And so another question you might ask is, how is this different from Interstellar? And so other than it being a real picture, I guess I've actually heard one other big difference is that, depending on how you count it, the Interstellar actually costs more money than the EHT. But actually, they got it pretty correct, except for Interstellar did choose to take some artistic liberties. So they actually ignored what is called Doppler boosting. And in Doppler boosting, it causes the gas that is coming towards you to actually be brighter than when it's moving away from you. So what this tells us for the EHT image is that actually the black hole is spinning. We know from the jets that the jets are nearly pointed at us, not exactly, like at about 20 degrees. But the black hole is spinning away from us such that the gas on the bottom is coming towards us and the gas on the top is going away from us. So we can kind of get the spin from the black hole that way. Another interesting thing is that if you look at the black hole over the course of the week that we observed at, you might notice there's some variation. There's some evolution. So I'll play it for you here. And I'll play it one other time. So we don't have a good idea exactly of what is causing this variation. It could, we don't know if it's just orbiting material or it's material that's lighting up. And we're even unsure exactly how it appears in the image domain. We want to be very conservative with what we say how it's changing in the image. But what we are very sure of is actually that variability exists. And that's because it appears in the raw measurements we take. So if you look at the closure phases over the different days, you'll notice that there's actually a huge difference in some of the longer baseline closure phases, so those high-frequency closure phases. And so that tells us that actually something has changed. It has been evolving. And actually getting a hold on time variability is quite important because the space-time around a black hole is actually by the no-hair theorem defined by only its mass, described by only its mass, its angular momentum, and its charge. And in fact, there are no other hairs or details of a black hole that kind of need to be taken into account when we're describing its effects on the environment. And so astrophysical black holes actually are expected to have no charge, so really only mass and spin matter. But getting a spin directly from an image is very difficult. And so observing an evolving source can help us in our quest to confirm or reject a GR. And although M87 is absolutely wonderful but it is actually really large, so that means its orbital period, the time it would take gas to orbit around it, is actually 4 to 30 days. But on the other hand, Sagittarius star, which is the black hole in the center of our own Milky Way galaxy, is a relatively small black hole, only 4 million solar masses, and that makes it so that the orbital period is much shorter. So you actually have a full orbit every 4 to 30 minutes. And that means that over a night of observing, we see a huge amount of evolution over the black hole. And that would be great if we could recover that in order to learn something about spin. Of course, it is much harder to recover something that is evolving over the course of the night from this really sparse noisy data. But simulations of reconstructions of Sagittarius star with the ground-based array don't actually give us much detail of this evolution. And so we're actually thinking for the future, considering adding space dishes to the array so we can carve out these huge swaths of space in the frequency domain very quickly and start to even recover movies of black holes over the course of a night. So we can see them quickly evolving, breathing over the course of minutes. And so really we're just at the beginning here. Now that we have this extreme laboratory that allows us to test GR, we can think of all the different ways that we can improve our instrument, improve our algorithms in order to further test it and learn even more. And so with that, I'll show one final simulation that shows the images that's coming into view as we add more and more data that we collect over time. So thank you.
We have time for questions. There are microphones you can stand up to so everyone can hear your question.
I know wormhole is very similar as black hole.
Sorry, it's hard for me to hear.
I know wormhole is very similar as black hole. How do you distinguish a black hole from wormhole?
So first of all, I'm not a black hole theorist, so don't ask me too much. But a wormhole for the same size mass, we know that its shadow would appear smaller. So here it's showing in the blue dotted line, that's what a wormhole would be for a 6.6 billion solar mass black hole. And I mean, for something that is 6.6 solar mass wormhole. And we know that you can't make it bigger than that because from the stellar orbits, we know that there has to be at least that much mass contained in that region. And so that is so if you overlay the image over top of these different circles, you notice that the wormhole is too small. It's too small to be the image of the black hole is much bigger than what you would expect for a wormhole.
Hi, beautiful, beautiful work. So I have several questions about sort of the combining of the information across the different algorithms and the different centers and so on and so forth. You basically said that the uncertainty outside the central circle is much, much greater, and therefore all these things that are sort of spewing out should probably be discarded. But they're kind of
very weak here, yeah. But you see, like if you look at it very closely, there's little tendrils of things coming off.
Yeah.
So that part you shouldn't believe very much.
Exactly. So my question is, I'd like to believe it somehow. So basically what I'm curious about is if instead of sort of looking at the uncertainty of any individual pixel, you could look at the uncertainty of the particular features. In other words, if you see a line spewing out for each of them, can you somehow say that the model of there being something spewing out is now having more certainty, even though we're not quite sure about how exactly and where exactly it would be spitting out? Do you see what I'm getting at?
Yeah, I would just be really careful. I mean, usually in these kind of imaging, you're limited by the SNR of your points. But actually, because we have such small amount of coverage, then actually we're more limited by UV coverage, more the frequency coverage. And so actually you can get common features that appear just because it allows you hide within the coverage areas that we're not seeing. And so you just have to be quite careful. And what we put out, we wanted to be very conservative with. Yeah.
The other question that I had is related to this averaging. It sounds like what you put out is some kind of average of the different images, and I'm just curious if there's another space where you could have done that averaging that would have preserved more information about the underlying.
Yeah, I mean,
process.
it was a big conversation, honestly, over months of what we were going to put out. Like if we wanted to put out a whole collection of images, if we wanted to put out one image, if we wanted to put out a blurred image, an average image. This was a big discussion because we wanted the world, people who didn't work on this, to understand the image, but not overinterpret it too much. And so actually, if you look at the paper, you can see all these different images and with the different assumptions and these different slices of parameter space, what image you get from them. But we thought that it was best to just basically blur it to, we expect from, let me see if I can get this UV coverage plot again. from here, you expect some maximum resolution at 25 microarcseconds. And actually, we blurred them to 20 microarcseconds. So we're kind of removing anything that we would get from super resolution. But we do expect that we would be able to achieve some super resolution in our images. So there's some level that you should believe them. Did that answer your question?
Absolutely. Okay. Now, I mean, no one else is standing up, so please stand up if you have more questions. So about these telescopes that are orbiting Earth, I'm just curious if you have, if the further you go, the more information you will get, or does it still matter that it's sort of close to Earth somehow?
Yeah, so what we wanted is that we wanted to fill in that UV coverage space really fast, so that we actually don't have all that uncertainty in the spatial frequency measurements we get. So for that, we would need it low Earth orbits. But actually, if you notice here, here is a plot of the shadow diameter for different black holes, and you can see Sagittarius star and M87 meet what we, at 1 millimeter, which is 230 gigahertz resolution, what we can see with the Earth-sized dish. But actually, if we go to longer than Earth-sized diameters for space dishes, we can pick up a couple more of these other sources. So actually, that is something that we're thinking about for the future, too.
So I've been reminded that there is a class here now, so we have to stop. But thank you so much, Katie. It was wonderful.
Oh, wow. Thank you so much.